Perhaps my favorite discrete probability distribution, if for no other reason than its name, is the Poisson distribution. A Poisson distribution models events that occur within a fixed interval of time, such as number of cars arriving at an intersection within every hour. We can also use a Poisson distribution to model events occurring over a fixed interval of space, such as number of leaks that occur per mile of oil pipeline. If you're familiar with the movie The Little Mermaid, you may recall the chef singing about Le Poisson, Le Poisson, and you may have drawn from that Poisson in French means fish. However, the Poisson distribution was not named after a fish. It was named after French mathematician Monsieur Simon Denis Poisson, who, if he was American, we would probably call Mr. Fish. What is unique about the Poisson distribution is that the mean and the variance in a Poisson distribution are equal. Let's take some examples of when we might use a Poisson distribution. If we're modeling the number of service requests received per hour at a phone bank, the number of misspellings per page on a student paper, the number of defects per 100 feet of wire, or the number of knots in 8 feet of pine 2x4 lumber. And I can tell you from being at the lumber store recently, the number of knots seems to have increased exponentially, if not on a Poisson distribution. Or the number of emails arriving in your inbox every 15 minutes. Those are the kinds of examples in which we would use a Poisson distribution, but there must be certain things that are true before we can actually use this distribution. Therefore, what are the properties of a Poisson distribution? Number one, the experiment must be based on fixed intervals of time or of space. And these we will call trials. The outcomes may assume an infinite sequence of values for each interval, with a minimum of 0 and a maximum, theoretically, of infinity. The probability of any occurrence doesn't change for any two intervals of equal length. And the occurrence or the non-occurrence in any time interval is independent of the occurrence or non-occurrence in any other time interval. The fact that a certain number of cars arrives in this hour should not influence the number of cars arriving in another hour. It may be that the number of cars is lesser in the middle of the day than at rush hour, but the arrival of the cars in midday is not influencing the arrival of the cars later in the day. For our business of the week, Dante has a real treat for us this time. If we want to use a Poisson distribution, what better place than going on a rafting trip? Dante tells us that in the afterlife, the ferryman shuttles souls across the river. The ferryman, Charon, takes 15 minutes to ferry souls across the river Acheron. Arriving souls must wait when they reach the riverbank. Charon has calculated that he ferries an average of 10 souls across the river for each trip. What is the probability of 5 souls arriving in the 15-minute period of time that Charon is making each trip? Is this in fact a Poisson experiment? Let's find out. Number one, is it based on fixed intervals of time or length? Well, yes, we're using 1-minute intervals. Are the outcomes an infinite sequence? Again, yes. The number of arrivals at the shore could be 0, 1, 2, 3, 4, 5, theoretically up to infinity. Does the probability remain the same from trial to trial? Again, yes. The probability remains the same of 10 per 15 minutes on the average. And are the trials independent? Assuming the randomness of death in the real world, then yes, the arrival of souls would be independent. At least we'll hope so. And as before, Microsoft Excel does have a function for a Poisson distribution. And yes, I have created an Excel spreadsheet that we can use to calculate Poisson probabilities. We'll explore that in our next video.